will start the module 4, that is laser, and then the quantum mechanics. You know what is a laser? It stands for LASER, laser. What do you mean by LASER, laser? It is the light amplification by stimulated emission of radiation. So L stands for light, A amplification, S stimulated emission, and R is for radiation. Now today, to start with laser, let us briefly describe the about the laser and its history. Then we go for the absorption and the emission processes. Finally, we'll come to the definitions of Einstein coefficients. So now LA is your laser on the right hand top corner. You have see there is a different colored lines. Actually, they are the laser of purple, blue, green, red, etc. are seen there. So now you know that is a laser. So LASER, laser stands for light amplification by stimulated emission of radiations. Lasers were the outstanding inventions of the present 20th century. It is not simple an amplifier. You have seen in the this LASER laser, it is said amplification. It is not simply an amplified one. It is actually the generator of light. So in the nature, you don't get the laser source as the natural one. It is the one created, that is one created by man. It's a man-made technology. Laser is an artificial source of light. So that is before actual the lasers that is came to practice in the year 1960. Actually, in the year 1960, T.H. Myman built the first laser. So to realize this laser, before that, there is some, that is Einstein gave an explanation to, that is he gave the theoretical background. There is the probable existence of laser is given by the Einstein in the year 1916. In the 1954 is what the Einstein, since Einstein gave that it is a possible light of source like a laser can be generated, it was realized practically by C.H. Towns, and that was called maser. Here it is not light amplification, here it is the microwave amplification. First it was microwave amplification of laser was introduced of laser in the year 1960 by Meinman. And today the lasers are used in almost in every field of life that is used by, and that is used in the medical field, in the entertainment section. So the lasers are used to do surgery, to create holography, that is three-dimensional image of an object. They are used in communication. You have seen in the last module, lasers are used to send information through optical fibers. They are used in industry to cut the weld and the drilling of metals and materials can be done. They are also used in the military to identify the enemy targets that may be flying over in the atmosphere. Look at the two diagrams. One is with the torch, left hand side, and other side you have a different color of striped these lines. So they are actually the lasers of different wavelength, different colors. So you look at when you look at the diagram, you'll get a feeling of what could be the laser. See, in the first diagram, a man is holding a torch and he is put on the torch, and look at the light that is diverging. It is spread over. And look at on the right hand side, there is a laser, nothing but they are the lasers. You have the fine beam of light. They are say one is blue, one is red, other one is purple, something like that. So each one is one particular color. They are in the visible region. So each line of light is possessing a one particular wavelength. Therefore, lasers are monochromatic source of light. Look at the left hand side. The man holding a torch. It was on. That is the white light. So it's the white light, and it is a polychromatic source. You have a laser light. So Laser lights are monochromatic in nature. Ordinary light, when you switch on the lamp or a tube light or any light that you use at the home, are nothing but the polychromatic sources of light. So you understood the laser. Let us come to the characteristics of laser now. See, the lasers, I told you, it is a monochromatic source of light. Lasers, they are never be polychromatic. The light that is coming out of a laser is having a single wavelength. They are the monochromatic source. See, this here the monochromatic is such that you don't get. I mean, if there is any impure wavelengths, it's only very small percentage. That is, the purity of the laser goes up to 99.99, something like that. So out of 100 photons, you may expect not even one photons available with such a deviated wavelength. Lasers are they almost 100%, almost 99.99% pure form of wavelengths. So all the photons that produced from a laser source possess almost exactly the same wavelength, but possess the same wavelength. There will not be much deviation from the wavelengths. Because of this monochromaticity, here all the photons you expect in laser that all the photons are expecting to be move in single line. See, in our ordinary source of light, that is, if you switch on the lamp, entire room gets glow, isn't it? So here, the photons are released in all possible directions. The photons released are in all directions. They have been released in all directions. The movements are random. In case of laser, all the photons they have released, they are possessing the same direction. All the photons that have been released possess the same direction. An ordinary source of light is take place in all possible directions, but laser travels in only one direction. All the photons are released are moving the parallel, uh, parallel. They are moving parallel. Because all the photons they move in parallel, certainly the the intensity will increase. Therefore, laser light is very intense beam. Here intense is such that suppose if you have a 1 milliwatt output of a laser is equal to your 1000 watt bulb. Such a huge intensity is available with a 1 milliwatt of laser because of its directionality. So since all waves are the photons are moving in the same direction, it serves as a very good laser. I mean, it serves as a very good coherent source of light. You know what are coherent source of light? So laser can be used as a good coherent source of light. So you understood what a laser is. Laser, it is light amplification by stimulated emission of radiation. I told you. Here the emission is not an ordinary emission. It is the stimulated emission. Ordinary emission takes place from a ordinary source of light. Any lamp that you burn, even the light, whatever you burn at home, they are all ordinary source. So the emission that is coming out, the photons that is coming out from such a source is cannot be stimulated one. They are not the stimulated ones. So for a laser, it's required to be for a laser it requires to be stimulated one. So now when you imagine you got a so some light of source when it is made to incident on a material, what will happen? The photon either is absorbed or the photon gets scattered. In some cases, you may have both the absorption and scattering of the photons. That is, when light incidents on a material is incident on a material, these photons either is absorbed or scattered, or it can be both. Both absorption and scattering might take place. Light absorption means it is a transfer of energy to the atoms. See, when light is incident on a material means it means what? The light gets absorbed by the atoms. As the result, as this particular result, the intensity of light is decreased. Since the photon that is falling on the substance, these photons have been absorbed by the atoms, so certainly the intensity releases, decreases. Once the photons absorbs this energy, what happens? These atoms here got the energy. They don't continuously accumulating energy, or they don't these atoms don't remain in the same state of higher energy throughout. I mean, for a quite long time. It has to give this energy that is absorbed by the system. So now this energy from the atom is given out. The energy that is given out from the atom to the outside, that is, understand. So now energy is given out from the atoms. If you go with classical physics, you don't get the complete understanding, you don't get the satisfactory answer for this, that light, the transfer of energy from atom as a light is not conceivable under classical physics. Therefore, quantum mechanics is used. Under quantum mechanics, you can see that the atoms, they give energy back. That is can be seen with a proper explanation. Therefore, we need to make use of quantum mechanics here to explain the transitions, or the getting the energy out of the atoms that have been excited. The transfer of energy from atom to light results in the amplification. We already said in the laser, the acronym LACR, where A stands for the amplification. So the transfer of energy from an atom is results in the amplification. We'll see that. So a laser, now so far we understood a laser is a monochromatic coherent source of light, and we need to understand the quantum mechanics in order to understand the process of how the photons have been will be released from the excited state. So in order to give an explanation, in the 1916, Einstein used a new concept of emission, that is called the simulated emission. In the year 1916, Einstein, in order to explain the overall process of laser, he introduced the term stimulated emission. See here, it is not simple emission, it is the stimulated one. Okay. So in order to balance between the matter and radiation, you know that E equal to mc square. On one side you got energy, on the other side you got a matter. To balance this, we introduced the word and the concept stimulated emission, that is used in lasers to explain the emission, overall emission, the amplification of emission. Okay. So now when radiation interacts material, so these are the probable processes. The first one is absorption. We have made that the second one as emission. Here now we split into two kinds of emission. One is spontaneous emission, and other one we will call it as a stimulated emissions. So now when light incident on a material, it is absorbed, then absorbed energy is given as emission. This emission may be spontaneous or stimulated emission. So emission is split into two categories. One is spontaneous emission and stimulated emission. So now, 1 minute. One minute. One minute. Due to some network problem, it is not displaying here. Yes, it has come now. So now we have three processes, probable processes when light incident on a material. The first one is, we call it as induced absorption. Look at the diagram on the right top corner. I will here to explain this absorption emission or emission. I use two energy levels, that's E1 and E2, for to make our understanding easier. We will take only two energy levels for any atom or material. You don't have just two levels, E1 and E2. There is plenty E1, E2, E3, E4, 5 up to En levels. For simplicity, for our understanding, to explain the concepts here, I'll just take the two levels, E1 and E2. Still there are many. Okay. So for me here E1 is the lowermost state. I may call it as the ground state. E2 is the next excited state. Now a photon is, look at the red. The photon is incident in the incident is going to incident to the system where the atom is in the lower energy state. So now atom or a particle is sitting at E1 now. When under such a situation, a photon is incident on that. This photon is picked by the atom. So the photon is absorbed by this atom or an electron here and gets moved to the E2. By absorbing a photon, now the particle is moving to level E2. It got excited. So now the particle in the E1 state absorbs a photon and moves to the excited state. So here, what type of photons they are going to absorb? See here, you are giving. I mean, you have a source outside. This source contains a large number of photons. It may have a photons of different frequencies. All those frequencies will not take part in absorption here. Only those photons whose energy difference is exactly equal to E2 minus E1 is absorbed here. If suppose any other photon whose energy is greater than E2 minus E1 will not be absorbed, or any photon whose energy difference is E2 minus of E1 is less than that, it will not be absorbed. Only those photons whose energy difference is exactly equal to the difference of E2 minus E1, they are going to be absorbed here. All other photons won't absorb. So only such photons are absorbed by an atom or electron that is sitting in the lower state E1 and moves to the excited state 1. So when it is absorbed, the photon is absorbed, certainly photon is disappeared and the atom moves to the higher state E2. So you look at here, there is a transfer of energy, that is a balancing of energy and the matter. So energy, photon is energy that is picked up by the electron or atom in the ground state, moves, so it is gets converted into its mass. So photon is disappeared. Now here in this particular transition, photon is absorbed. Such a process is called the induced absorption. Induced absorption is a process where a photon is absorbed whose energy difference is exactly equal to E2 minus E1, and the particle or an electron that is excited to the level E2. Such a mechanism is called the induced absorption. So now the atom A, if you imagine the atom A got excited to the state A star. So A star refers to the state of excitation. Look at the above expression, that is A plus H nu is equal to A star. That tells you that A is the atom in the ground state. A represent, it is an atom in the ground state. When it absorbs a photon H nu, goes to the excited states. So induced absorption is given by this expression A plus H nu is equal to A star. So we express induced absorption is equal to A plus H nu is equal to A star, where A is the atom in the lower state and A star is the represents its excited states. So now, how many such photons in absorbed in any induced absorption is given by NAB. AB, so the subscript AB refers to the absorption. N is a number. So NAB is equal to B12 N1 U gamma and delta T. I'll explain this. See here, imagine a system of n number of atoms. So there's n number of atoms, and you expect the energy levels to be n, 1, 2, 3 up to n, and under normal conditions, there are imagine there is 1,000 atoms are there in a system. All these 1,000 atoms do not possess, they don't remain in the one state. That is, all these 1,000 atoms need not be present in the E1 state. So the distribution of atoms takes place into various energy levels. That is, out of 1,000 atoms, not all that 1,000 will be remaining in E1. Some, let us say 500 is in the E1. Then another remaining 300 may goes to level E2. remaining 100 are maybe go to E3, another 50, 20. It's like that. It gets distributed into various energy levels. So all these 1000 photons are distributed into various energy levels such a way that always the lower levels, if you call E1 is the lower level with respect to E2, this E1 contains more number of atoms than that of N2. If you take the level E2 and E3, E2 is the lower level and E3 the excited level, higher level. When you look at the number of atoms between E2 and E3, E2 got more and E3 got less, like that. So always lower levels are occupied with more number of atoms. As you go up, the number of atoms kept on decreasing it. Though the energy is increases, E1 is less than E2, less than E3, less than E4 and so on, but the number of atoms they get decreased as you go above. N1 is greater than N2, greater than N3, greater than N4 and so on. So therefore, there will be more number of atoms available at the lower levels. So now here we are looking at the induced absorption. For an absorption, for induced absorption, we see that the photon is being incident at an atom that is sitting in any one of these levels. For simplicity, we consider two energy levels, E1 and E2, and imagine that number of atoms that they are staying in the level E1 is N1 and then at the level E2 is N2. So N1 is greater than N2. That is a normal condition. Under normal condition, number of atoms at N1 that is in level E1 that is N1 greater than N2. That is the normal procedure condition. So now the photons have been absorbed. What is that? What are those such photons they absorb? Whose energy is exactly equal to E2 minus E1. Out of n number of photons available, all those n number of photons need not be having the same energy. They got different energies. So only those photons whose energy difference is exactly equal to minus E2 minus E1 is that only such photons are absorbed. So that number of photons is given by U gamma here. Look at the expression U gamma. U gamma represents only those photons whose energy difference is exactly equal to E2 minus E1. If a large number of such photons are available, all these photons may take part in the absorption process again, and it depends on the number of atoms they are present at E1. If N1 is the number of atoms present at the level E1 and U gamma is whose energy difference E2 minus E1 is incident, then these photons absorbed. Therefore, the number of absorbed photons, the probability of absorbed photons is given by a constant is given by the expression NB proportional to N1 U gamma and delta T. It means the number of photons that are absorbed in this particular situation is proportional to number that is available in the level E1 and the density of the photons in time delta T. So that is this proportionality constant is given to, later on we call it as the Einstein coefficient for induced absorption. We'll see that in the next slides. So the rate of absorption. So rate of absorption is the number of photons. It defined as the number of photons absorbed per second per unit volume in the material from the state E1. That is equal to V1 to N1 U gamma. So in the previous slide, we have seen that the probability of the absorbed photons that have been absorbed, that is equal to B1 to N1 U gamma delta T. So if you divide that AB, that is number available per time delta T, you will get the rate of absorption. So the rate of absorption is the rate of induced absorption per unit time per unit second from the level E1, that is B1 to N1 U gamma. So I told you this B12 is nothing but the Einstein. It is called the Einstein coefficient of induced absorption. When the photons in the lower level is more, and the number of photons that have been incidenting on this particular level is more, you expect the more atoms to be excited. Okay, more atoms, more atoms are available at n1 and more photons are incident at n1. Therefore, you'll expect more atoms to get excited. Okay, this is about the induced absorption. The next consequence when light incident on the material, the one probable one is the spontaneous emission. Look at the diagram. So the atom is already got excited to the energy level. See, in the previous discussion, you have seen that atom absorbs energy and moves to the excited states. Now that is the excited state now. Excited state now. So when it is in the excited state, that excited state is not permanent state. It's not permanent state. It will come down to the lower state with the emission of photon. So the excited state is not the permanent state. This excited has to descend to the lower state within certain time. So beyond that, it cannot remain there. So within a short time, is almost equal to 10 to the power minus 8 second. Within 10 to the power minus 8 second, the excited state will come down, descends to the lower state with the emission of photon. So here, the emission of photon is taking place voluntarily. It is not been helped by any other mechanism here. So the atom now, which was excited to the excited atom or electron that is excited, that will come down to the lower state at any time as it likes. Okay, that is the spontaneous emission. So here in spontaneous emission, look at the expression there. A star, it means it is the excited atom, comes down to the ground state, that is A, with the emission of photon. This is voluntary, no help is taken out by this transition. Okay, so now when atom got excited to level E2, it can stay only in a time 10 to the power minus 8 second. Thereafter, it will come down with the emission of photon whose energy equal to h nu. Therefore, the emission of photon occurs to the lower state on its own without any help, no other help. It is taking place voluntarily to the ground, the lower states. This overall process is called the spontaneous emission. Spontaneous emission is that process where the excited state returns to ground state, lower state, with the emission of photon voluntarily without taking any help is called the spontaneous emission. Then rate of spontaneous emission, you see that you have seen in the previous diagram that it's no help is taken out. So it's only the photons coming down. Therefore, rate of spontaneous emission depends on the number of atoms that are available in the state E2. Here N2 is the number of particles or atoms or electrons available in the state E2. Now these N2 number gets released to the lower state with the emission of photon. And the rate of emission is, as is seen before and is seen learnt before, it is A21 N2, where A21 is the proportionality constant, that is called the Einstein coefficient of spontaneous emission. The number of spontaneous emissions can be given by is NSP, that's equal to A21 N2 delta T is the time. So this is the probability of spontaneous emission. The rate of spontaneous emission is you need to divide by dt, that is dn by dt. That will give you the rate of spontaneous emission, that is equal to A21 N2. In spontaneous emission, the emitted photon will be at random direction. I told you it's if you look at an ordinary source of light, at a source of light, they are the uh, uh, incoherent in nature. So the spontaneous emission results the emission of photons at random directions. It is not directional. They are incoherent in nature. The third consequence, if not a spontaneous emission, it could be a stimulated emission. Look at the diagram. In stimulated emission, the atom is already excited to the state E2. Now it is in the excited state now. It is held by an external passing photon. When there is an external passing photon, again the energy of this photon should be equal to E2 difference of E1 is equal to h nu. Say the passing photon, the one which is going to hit the excited atom at E2, should have an energy difference equal to E2 minus E1. Only such photons have been will take part, will initiate the stimulated emission. Now this passing photon in the level E2 is in the level E2 hit the this particular atom and does the ground downward transition. So now the difference between these energy levels E2 minus E1 is released as a photon. So now there is one passing photon and the difference of these two energy level, because of the downward transition, another photon is released. Here these two photons are identical in nature. See, I told you the energy difference of E2 minus E1 is created as a photon. So now this happens only from those photons again whose energy is equal to exactly equal to the difference of E2 minus E1. I told you in a beam there may be n number of photons with n frequencies, different frequencies. All those photons will not take part here. Only those photons whose energy difference is exactly equal to the difference E2 minus E1, only such photons will initiate the stimulated emission. Therefore, now these two photons bear the same in all respects. They are identical in all respects. Two identical photons. They are just like twins now. They move in the same direction. That is the speciality of the stimulated emission. So now these two photons, they move in the same direction. That is this is the speciality for the laser. In a laser, all the photons, they move in the same direction. They are unidirectional. Because of this unidirectional, they creates more energy, more intensity, and hence since all the photons have been having the same they are identical in all respects, therefore it can be treated as a coherent source. When an atom or an electron in the level E2, I mean in the excited state E2 interacts with a photon whose energy equal to h nu, this photon induces the excited atom to make downward transition well before the atom can make spontaneous transition. See, before happening the spontaneous emission, you can achieve the stimulated emission because of the external passing photon whose energy difference is exactly equal to E2 minus of E1. The atom emits excess energy. I told you the excess energy between E2 minus E1 is given out along with the passing photon. The phenomena of the forced photon emission. Here the photon is emitted out not by voluntary, it is forced, it is the forced emission by an external passing photon. So the difference in these two energy levels is one photon and the passing photon is another photon, they go together in the same direction. So this is called the stimulated emission. This process can be explained by this expression A star is plus h nu is equal to 2 A plus 2 h nu. Here two photons have been created. A star is the excited state, comes down to the ground state as A. The probability of stimulated emission is given by this B21 N2 U gamma and delta T. That is the number of emissions, probable emissions. Again, rate of emission is the dNST by dt. So if you differentiate the NST by dt, it will give you the rate of stimulated emissions. In rate of stimulated emissions, it is directly proportional to the number of atoms that are available in the level E2 and the photon, that is the passing photon density, that is U gamma. Their proportionality constant is given by B21. It is called to be Einstein coefficient for stimulated emissions. So in every process you got one proportionality constant. In the induced absorption case you got A to 1, it is called induced Einstein coefficient for induced absorption. In case of spontaneous emission you got the proportionality constant, that's called B12, called the Einstein coefficient for spontaneous emission, and in the third case here B21 is called the Einstein coefficient for stimulated emission. All these coefficients are the nothing but the probabilities. So in any transition you cannot say you cannot because there is n number, a million number of atoms are available, you cannot count by numbers 1 2 3 4 5 6 etc like that. So the number of probable absorption or the number of probable emissions are given by these coefficients A21, B12 and B2. The Einstein coefficients, they give the probabilities associated with the absorption processes and as well as emission processes. So this completes today's discussion.